Okay, question 18a reads, a matrix K is defined as K is equal to 3i. Write down matrix K and describe the single transformation it represents. So it's important to note that I in matrices represents the identity matrix. That's one of my weird little eyes. And the identity matrix is 1, 0, 0, 1. And effectively, this is a transformation that does nothing. It transforms a point onto the same place. We want K, which is 3 lots of the identity matrix. It gives us a space to do that. And 3 times that is simply 3003. So nice and easy. It also says, describe the single transformation it represents. So the transformation of whatever this number is, and as long as these are both zeros, this is an enlargement by scale factor. And whatever this number is, that will be your scale factor. So you need a sentence underneath. It's an enlargement by scale factor 3 about the origin. I think you can get away with not saying about the origin, but it's good to put it in there. All matrix transformations are always about the origin. Question 18b. Point A is mapped onto point B using the transformation M followed by the transformation N. Transformation M is a 90-degree rotation anti-clockwise about the origin. Transformation N is a reflection in the line y equals negative x. Find the overall transformation matrix T that maps the point A to point B as a single transformation. That is quite a wordy way to ask that question. However, effectively, it means this. You've got a transformation here and it acts on a point. Then you've got a second transformation afterwards. And rather than do 2 separate transformations, is there an overall transformation effect that could just be done in one transformation? So to do this, you need to find the matrix of transformation A, M, and the matrix of transformation N. Some teachers just tell you to memorize what the matrices are for these transformations, and if you have, well played. Fair enough. But there is a way to work it out if not. If you've not seen this, it's going to look a little bit weird. So for transformation matrix M, so we mark on the points A and B, and this will always, A will always be 1, 0, and B will always be 0, 1. And that comes from the identity matrix, 1, 0, 0, 1. All coordinates are written in column vectors. So the coordinate 1, 0 is actually written as a vector 1, 0. Confusing because it's very easy to think, oh, it's 1, 0. But all coordinates are always written as column vectors. I'm just going to put that on to make it clear. And here we've got the point 0, 1. And again, B is written as a column vector 0, 1. And we're going to transform both of those points. So we're going to literally rotate them 90 degrees clockwise about the origin. Point B would end up here. And I'm going to label that B prime. We often use prime for transformations. Okay, so that coordinate it's transformed to is negative 1, 0. And A would actually rotate on top of where B originally was. So I kind of just put a point there, kind of on top, and I'm going to label that A prime. Right, your matrix will be the column vectors of the new transformed points. So A prime is 0, 1, and that's written as the column vector 0, 1. B prime is negative 1, 0, and that's written as the column vector negative 1, 0. And that is the transformation matrix for a rotation 90 degrees clockwise about the origin. We can do the same thing for a reflection in the line y equals negative x for N. Start with A and B. We're going to reflect them in the line y equals negative x, which is that line there. A reflects to here, which is A prime, and that's the point 0, negative 1. B reflects here. That becomes B prime, and that's the point negative 1, 0. So my transformation matrix is the column vector of A prime, which is 0, -1, and it's the column vector of B, -1, 0. And that is the transformation matrix for a reflection in the line y equals -x. Now, to combine transformations together, you do not apply the first transformation matrix first. The transformation matrix T is we do transformation matrix M first, then we apply transformation matrix N to transformation matrix M. Multiplication in matrices is not commutative, so you can't swap the order around. So you've got to kind of do this reverse thinking to it. After you've done that, it's just matrix multiplication. 0 times 0, add -1 times 1 is -1. 0 times -1, add -1 times 0 is 0. -1 times 0, add 0 times 1 is 0. And -1, add 0 times 0. -1 times -1, add 0 times 0 is +1. And that is the final transformation matrix. There are a couple of different alternative methods to doing this, but this is the final answer. And we're done with that question. Question 19 is a large question and reads, the triangle ABC has lengths AB equals 9 centimetres, BC equals 11 centimetres. We're told that the area of ABC is 47.6 centimetres squared and that angle ABC is obtuse. Find the length AC. Well, we've got an area and we're probably going to be able to have to work backwards to find this missing angle in between the two lengths. Our formula for the area of a scalene triangle is the area is equal to, area, not very well written, area is equal to AB sine C. But really that just means the angle in between two lengths, which we have here. And then to find this opposite side, once we've found the angle, we're probably going to need to apply cosine rule. So we've got A squared equals B squared plus C squared, take away 2BC cosine capital A. And again, capital A is the angle in between B and C. Sometimes these letters get all mixed up, but really it's the angle in between B and C. And lowercase a is the opposite side. Okay, if I was to label all of that, and maybe let's write a better version of this formula. If we write BC sine A, then we can more appropriately label this as capital A. This would be little side A, this would be B, and this would be C, although B and C don't really matter. Okay, putting them into the formulas, we're going to get that the area is equal to half times 9 times 11 times sine of the angle. And I'm just going to go with theta for the angle, but that is capital A. Okay. Then we can actually work this out, half times 9 times 11, and divide both sides by it. So divide by 49.5. Then to find the angle, we're going to do the inverse sine of that, and that's going to give us 74.07. But we have a problem. We're told that the angle ABC is obtuse. So this is a rare situation where you're going to have to find the alternative angle that sine could be. And you have to use the formula that sine of any angle is also equal to sine of 180 subtract that angle. You could have a potential of two different answers. So to find the obtuse angle, you do 180 multiplied by this principal angle here. And that's going to give you, I've clearly done that wrong, so I'm going to pause and fix it. Okay, so I fixed my mistake and I found the obtuse angle 105.93. And you can see why it affects the next question because we're going to need to use cosine rule on this angle. So my opposite side AC, which we could have labelled with A, but I did it for X when I did this before. That's confusing as well. That's equal to 9 squared add 11 squared, take two lots of 9 times 11 times cosine of the angle. There's my mistake before. Nothing wrong with making mistakes as long as you know how to fix them. And then I've just taken the step of square rooting it all afterwards. And because it's a calculator, you can just type all of that in as it is, if you've got a good calculator. And that should give you the length is 16.01 centimetres. This obtuse angle one really does catch people out, so just be careful if they do use it, but it is quite rare. And we're done with that question. Okay, below is the graph y is equal to ab to the power of negative x. We're given two coordinates that lie on the curve, and they're -1, -1.35, and 2, -0.4. And there is a little typo there. Okay? All right, work out the constants a and b. Okay, so this is an exponential graph, and effectively all you need to do is substitute the coordinates into the equation. Be careful because it says -x. So for the very first one, our y value is -1.35 when x is -1. So we've got our AB, but I'm doing negative of -1. So be careful, that ends up as +1. So we end up with our first equation, -1.35 is equal to a times b to the 1. I don't have to write the b there as b to the power 1, but it will come in handy in a second. Equation 2 is going to be -0.4 equals a b to the power of -2, substituting in 2 and -0.4 for x and y respectively. Now, this is a type of simultaneous equation for a and b. To solve this equation, you need to divide the equations against each other. In general, you want to divide by the negative power. It makes it seem more complicated, but it'll make it easier afterwards. So we're going to do equation 1 divide equation 2. -1.35 divide -0.4 is 3.375. You could have also left that as a fraction. A divide A is 1, so that cancels out. And b to the power of 1, that's why I had it there before, divide b to the power of -2. We subtract the powers. 1 subtract -2 is 3, so we end up with b cubed. And that's what I have here. And then we just need to cube root each side, and b is equal to 1.5. And that's my first value to find a and b. And then all you have to do is substitute that into one of the equations from before. I'm going to put that into equation 1 because it's the easiest. So, -1.35 is equal to a multiplied by, well, b is 1.5, and to the power of 1, well, that's just itself, so we get that there. Divide both sides by 1.5, and we get a is equal to -0.9 or -9/10. Put it in the answer space below, and we're done with that question. Last question. Question 21 reads, the circle is on the xy plane. The circle has two tangents with given equations. The first tangent is at the point 0, 1, and has the equation y equals 4/3 of x add 1. The second tangent is at point 4, 3, and has the equation y equals 3. Find the equation of the circle. Now, what is tricky about this question is that it does not give you a diagram to help you visualize the question. And there is really a lot going on there, and it really isn't obvious how you're going to find the equation of the circle just from this information to start with. So draw a sketch of the diagram, which I've done here. I've marked on the points 4, 3 and 0, 1. I know there's a tangent at 4, 3, and I know that the equation of that tangent is y equals 3, which is a horizontal line. And I also know that the equation of the tangent at 0, 1 is 4/3 of x add 1. So that's kind of got a positive gradient and will probably look something like this. And therefore, my circle is going to be tangent to both those lines. So it's probably going to look something like that. Now, does it need to be perfect? Absolutely not, because it's a sketch, okay? But it's good to get your head around the problem. I'm just going to extend the x-axis to make it look a little bit better and label the x and y-axis. Okay, here's the key bit. We've got two tangents. The normals to two circles' tangents always meet at the center. That's kind of like a circle theorem. So, if I do a line that's perpendicular to the tangent, if I do that here, and if I do a line that's perpendicular to this tangent here, the intersection points of both of those normals to the circle will give me the centre of the circle, which I'm going to label as C. So what I want to do is I want to find the equation of both of those normals to the circle. And to do that, we're going to use the tangents to the circle. The tangent to the first one, y equals 3, should be fairly easy because it's going to be a vertical line. And it's a vertical line going through the x-ordinate of 4. So it would pass through 4 on the x-axis. So the normal to y equals 3 is just x equals 4. Then we want the normal to this here. The equation for the tangent was y is equal to 4/3 of x plus 1. Okay, so the normal will have a negative reciprocal gradient. So we flip the fraction over and apply the negative symbol. So that's going to be y is equal to negative 3/4 of x. But we don't actually know what c is. So you have to substitute a coordinate on that normal line to be able to find out c. Well, we know it goes through 0, 1. So substitute 0, 1 in. That's going to give you 1 equals negative 3/4 of 0, add c. This is just 0, so c is equal to 1. Actually, that really should have been fairly self-explanatory because that normal goes through the y-axis at 1. So the equation of normal is y is equal to negative 3/4 of x, add 1. Those are our two normals. They intersect at the centre. So you need to solve these two equations simultaneously to find x and y. Luckily, these are really nice to solve simultaneously because we know that x must be equal to 4. So we simply substitute x equals 4 into this equation here. Negative 3/4 of 4, well, 4 gets multiplied by this, just eliminates the denominator of 4. So I end up with y is equal to negative 3 add 1. So y is equal to negative 2. So this gives me a centre at x is 4 and y is negative 2. That's the solution to these simultaneous equations. So the centre is at 4, negative 2. But to find the equation of the circle, I also need the radius. Let's go back to the diagram and add the centre of that circle. That was negative 4, 2. We want to find this distance between the centre and the radius. Now, normally you'd use Pythagoras to go between 2 points to find their distance. However, this one's made a little bit easier for you because both coordinates have an x-ordinate of 4. So all you need to do is find the difference between, sorry, that should be 4, negative 2, apologies. You just need to find the difference between the y-ordinates. And the difference between 3 and negative 2 is 5, so the radius is 5. And so our equation of the circle is x subtract its x-ordinate centre, y subtract its y-ordinate centre equals the radius squared. And that is x take 4 squared, add y add 2 squared equals 25. A tough question, but we're done. Thank you for having a go at my paper. I hope it's been useful for you. Mr. Brennan signing out.